One, I am Pushpita Sanda. I'm a PhD student at IIT Delhi under IIT Delhi and University of Queensland joint PhD program. So today, I'm the TA for this course in Introduction to Lasers and Laser System. And today is the tutorial number 12, and I'll discuss the remaining part of the semiconductor diode lasers. Not only semiconductor diode lasers, the lasers that are used in semiconductor diode, they have different kind of name. So last week we discussed very briefly what is semiconductor. Semiconductor means that under certain condition, mostly in temperature, some materials behave as a conductor, but normally it doesn't behave as a conductor. So semiconductor materials exist both in elemental and compound form. The most popular element is semiconductor is silicon and aluminum. Elemental form and compound form. That is silicon from Germany. And the molecular variety or compound variety we have many things that is gallium arsenide, gallium phosphide, indium phosphide, and so on and so forth. So gallium arsenide and indium phosphide are in fact most widely used material for the operation of semiconductor laser. Both these varieties of semiconductors are also called intrinsic semiconductor, as the semiconducting properties are inherent to these materials. By virtue of their ability, semiconductors allow the conduction of electricity by both electrons and hole, displaying remarkable properties. So here they both conduct the electrons and holes. The presence of only a trace of impurities can significantly enhance the conductivity of the semiconductor. Semiconductor embedded with such impurities are called doped or extrinsic semiconductors. So we need to understand the difference between intrinsic semiconductors and extrinsic semiconductors. So they have the inherent property of electricity, but the extrinsic semiconductors, they need to be doped or any impurity or doping needed. So when you need to do doping, we need to select the dopant material very carefully. So it can be acceptor or donor. So when it is the donor, it is N-type semiconductor. When it is acceptor, it is actually P-type semiconductor. And for dopant material, can we do type or acceptor? When doping material is donor, the majority charge carrier is electron. The principal charge carrier is electrons. So it's called N-type semiconductor. Conductor. And when the dopant material is acceptor, the principal charge carrier are holes. And the semiconductor is called P-type semiconductor. So the best thing that always use N-type and P-type semiconductor and in contact. So the semiconductor reveals its true potential when the N-type and P-type semiconductor are made brought in contact with each other, and later we will see that more the junction or NP junction, more there is a junction, the more the merrier. So N-type semiconductor, before going into that, we first have a look of the lattice structure of an intrinsic semiconductor. So for an intrinsic semiconductor or silicon, this is a crystalline silicon structure. So you can see the silicon has valency of 4. In the absence of any loose or free electron, the silicon crystal will not conduct electricity unless some electrons from the valence band are excited to conduct it. All the silicons are here. See that as the silicon is valence 4, it will form a bond with these 4 electrons with other silicons. So there is no free or loose electron. However, if we dope the silicon crystal with a very little amount of arsenic with a ratio of 1 in 100 million. So we can see the semiconducting effect. So this is a crystalline silicon. So even if we put one arsenic 400 million silicon, that arsenic replaces silicon, and arsenic has 5 valence electrons. So the 4 will be occupied by neighboring silicon to form a bond with them, but there will be an extra electron, and this extra electron will start the conducting effect. The remaining 2 electrons move freely in the crystal, and the arsenic atoms here function as donor, and the principal carrier here is electron, and it can get easily into this electron can get easily into conduction mode. And this is an indirect semiconductor. And one need to remember that in room temperature there are few holes present in the valence band, because the few electrons from are excited from valence to conduction band, and it is basically the effect of temperature. But most of the electrons which are in conduction band are dominated by the arsenic atoms. So the bond structures are like this. So see here many electrons. This is arsenic doped silicon. This is the lattice structure. This is the band structure. This is crystalline structure. This is band structure. So most of the electrons in the conduction band are basically dominated by the arsenic, but here are some holes in the valence band, and the corresponding electrons are also in the conduction band, but this valence band, like this formation of electron and hole, is due to thermal presence of thermal energy in the system in the room temperature. And this is the corresponding crystal structure of the acceptor or p-type semiconductor. So the gallium in here works as an acceptor, and why it is called acceptor? Because it has the valence number of valence electron on the gallium has is actually 3. So with the 3 electrons, it forms a bond with neighboring 3 silicons. But it needs to form a bond with another silicon, the 4th silicon. For that, it needs to accept the electron from the silicon structure, and it by doing that, it generates a hole. So that is why it is called acceptor. So a hole will be present where a fourth electron should be. Here the majority carrier is holes. So this semiconductor is called p-type semiconductor. Okay. And this is the bond structure of a p-type semiconductor, that is clearly saying that the valence band has many number of electrons, and valence band has a large number of holes, and the conduction band has a few electrons, and that is also that for the thermal energy present in the room temperature or due to the thermal excitation. The reason is same why even though the majority carrier is electron for entire semiconductor, there are some holes in the valence band, and when the majority carrier is holes for p-type semiconductor, but still there is some electron in conduction band, and that is basically thermal excitation, due to thermal excitation. It's this crystal structure, the band structure. So this is basically very basic of different of semiconductor. Now we will go to semiconductor diodes. So if we join together a p-type and n-type semiconductor, that in P, so this form my NP junction, and this work as an NP diode. So when we do work with an NP diode, semiconductor, P semiconductor, some of the free electrons from the N region want to go to the P region, because the P region is deployed of electrons, and some of the holes of the P region is want to diffusion through the N region, because the N region has very few holes. So when they just want to move to the other side, they recombine. So you need to remember these electrons are present in the conduction band in the N region, and the holes are which are present in P region and is the valence band. So basically they are not moving like this. Here the electrons are here, the holes are here, so they recombine like this. The electrons jump from conduction band to valence band, and they recombine, and the both carriers disappear. So by doing this, what happened? Area adjacent to the junction in the inside, they will be deployed of electrons. So they will go as a positive sign, and the area around the junction in the P side, all the holes have been recombined with the electrons. So That is basically they form a negative charge there. Basically, this region is depleted region, which means there is only positive ions in the inside and layer of negative ions are present in the p side. This region with immovable positive and negative ions devoid of any electrons and hole and is called depletion region. Separation create a field. So they create an electric field here, and that electric field opposes any further diffusion of the charge carriers across the junction. Soon an equilibrium will be established. Generator depleted region will oppose any further diffusion. So an equilibrium will be established, and when the opposing field will be strong enough to put stop on any more diffusion. The results in establishing a thin region in the vicinity of the junction that is devoid of any carrier, and this is depletion region. So this open up interesting possibility of using PN junction. So till now we didn't have applied any bias. So now we have to consider two cases. Reverse bias situation. This is a reverse bias situation. The first one. And this is forward bias. So in the reverse bias situation, so N side is connected with the positive terminal of the battery and P side is connected to the negative side of battery. So what happened that this is the positive side of battery, so all the remaining electron which cannot diffuse to the part of P side because of this depletion region field will go into a now opposite direction towards the battery. And all the holes also go towards the battery because it is connected to the negative terminal. So there will be a momentary flow of current as the free electrons from the N region and the free holes from the P region flew away into the battery. And that's why we will get a tiny bit of current there. This quickly results shows what happened if all the electrons are moving this side and all the holes are moving this side. So the depletion region will increase. Basically, that's will happen. And thereby that after some time, the flow of current through the circuit will stop instantaneously. But there are some diodes like Zener diode and all. So in the reverse bias option, these go to a certain voltage where breakdowns happen and you will get an immense current there. So Zener diode always work as a reverse bias. The reverse bias mode. But we are not here. We are not discussing the Zener diode. We are discussing the normal diode, which will be used in a laser. So that's the thing that we need to understand that all those diode work as in the forward bias region. So what happened that when we applied forward bias, so the inside of the diode is connected to the negative side of the battery. So this negative side repel those ions. So the battery literally pumps electron in the in region and here they like they are moving holes in the p region. That means they are extracting those electrons or removing those electrons from the p region, or the same thing that p is producing more holes here. That means they are removing the electrons from the p side. This the holes and the electrons continue to meet, and now they have more number of electrons in n side and more number of holes in the p side, and they will recombine, and basically they will annihilate each other in this junction, and this junction will not like previously the junction has been with depletion region junction. They used to oppose this recombination of electron and holes, but now they are connected to the battery, and the battery is pumping more electrons and holes in both sides. So this depletion region will not be able to stop that recombination. So we will see the exponential growth of electrons. So this is the I and P characteristic graph of the PN junction in a reverse bias and forward bias mode. So we need to remember this like graph, that how this happens. So it's only zero when voltage is zero. Otherwise, even we give negative voltage or positive voltage, we will get some kind of current. If reverse bias, we will get much more less current. So we first discuss LED. So either in a conventional light or either the diodes produce conventional light or laser light. Laser is a very dense covalence light basically. So we need to know that there needs a photon that should be emitted. So in a conventional light also, like LED, this light emitting diode, so what happens that when an electron and hole, the electron is present in a conduction band and hole in valence band, when this electron and hole recombine, they will generate a photon, like the energy, the excess energy when they recombine, that will be carried by a photon. So a minimum amount of energy within the band gap energy is required to be imparted to a valence band electron for its excitation to the conduction band, leaving behind a hole. So before this stage, how we get to this stage, so the hole and electron has been created, that we need to have a minimum energy that is a little bit more than band gap energy. Then the electron will be excited and goes from this valence band to the conduction band, and it will create a hole and electron pair. Although the omnipresent thermal energy normally facilitates this excitation, it can also be achieved optically provided the photon energy exceeds the band gap energy. So now after that, the electron from conduction band falls into a hole in the valence band, and they annihilate each other, and the extra energy will be carried by this photon. And this photon will make the diode as a light emitting diode. That whenever the photon is there, the diode is producing photons. So basically it is a light emitting diode. So we can say that when a PN junction is in forward biased, it is capable of emitting light. But the thing is that electron hole transition is regulated normally for only direct band gap semiconductors. In a direct band gap semiconductor, the total momentum remains conserved of the electron and holes. And when this transition happens, that the electron jumps into the hole, the exchange energy is carried by the emitted photons. But in indirect bandgap semiconductor, what happened? The total moment of electron and the hole change as they recombine, and for that momentum cannot be conserved by releasing excess energy as a photon. So then the thermal energy kicks in and the energy is dissipated as heat instead of light. That is why that silicon cannot be used as a LED, because silicon is an indirect bandgap semiconductor and it's not a good light emitting diode, because for light emitting diode we need a direct bandgap semiconductor. Some of the light emitting, that gallium phosphide, aluminum phosphide, aluminum arsenic, aluminum antimony, they are all indirect bandgap semiconductor and they cannot work as a LED. Those diodes has other different kind of purpose. But here our goal is to know which diodes can be used in lasers. So for that, laser and any conventional light source that we use, the first thing is we need photons. We don't need the thermal energy. So basically for that, we need direct bandgap semiconductor, and the examples of some direct bandgap semiconductor is gallium arsenide, gallium antimonide, indium arsenide, indium phosphide, and indium arsenide. Of this, gallium arsenide has the distinction of emerging as the very first light emitting diode. That was first LED. So now we'll go to diode lasers. If we get LED, so basically a light emitting diode can be turned into a laser when forward biased current exceeds the lasing threshold value. That is, if we place it in a optical cavity and made other arrangement that the population inversion can be sustained, and there is optical feedback which is placing it in a cavity, we can change LED to diode laser. The population inversion can be ensured by appropriately increasing the pumping current so that the rate at which electrons fall into poles and recombine exceeds the rate at which electrons at a valence band can jump into the conduction band by absorbing photons emitted from the recombination. And feedback can be provided by placing the device inside an optical cavity. So basically this is an optical cavity, and this junction is basically active region. And we know that the reflective index of semiconductor materials is usually very high. Fresnel reflectivity for gallium arsenide is almost 32%. Keeping the end faces perpendicular to the laser axis will therefore allow much of the light created in the junction to be reflected back and forth. So the light has been created in the junction. And now these some photons that is spontaneously emitted, they will start at simulated emission and causing amplification of light. And that is how diode laser will work. So basically optical cavity has been created only in this position or somewhere like this. The active region is basically this junction. But here we cannot control. Basically we cannot control the carrier flow and the electricity flow. So then we will go to homojunction diode. So the diode lasers are different like homojunction diode laser and heterojunction diode laser. So we will see what is the problem using homojunction diode laser. Then we will see why we need heterojunction diode laser. So what is homojunction diode laser? The diode is made out of same type of semiconductor material on both sides of junction. So basically, we will see the cross-sectional in view like this. This is Peter gallium arsenide. Here is inter gallium arsenide. So both of the case it is gallium arsenide. One is Peter and another is inter. When the diode is forward biased and current begins to flow, recombination of electron hole pairs sets in across the junction, resulting in emergence of spontaneously emitted light. So the intensity of the light gradually increases, that we know when we will apply reverse bias. Oh, sorry, when we will have forward bias. In reverse bias, thing will not work basically. Like we will get very few. So the electricity will increase to a certain point, and then it will reach a critical value And then after that, there will be a dramatic rise. And this, so LED works in this position when they doesn't cross that I threshold value. And after it's like crosses the I threshold value, it is now working in the laser domain. So up to this point, this is basically LED region, and after that, this is the laser operation region. The requirement of this threshold current is exorbitantly high for a homojunction, that this point is at very high. So if the point is here, we will get very sooner the laser action. So to do that is I will have for homojunction direct laser. To reduce that I threshold point, we go to heterojunction direct laser. So here, what is the reason that I threshold is very far away? Because the light can accept easily here. Light can escape very easily. So it can accept both from the top and the bottom end, because their refractive index gallium arsenide is same from both sides, so they will not be trapped, and the carriers are also not trapped. One slide. So for these two reasons, they contribute to the extremely low electro-optic efficiency, and that is why we need to go to heterojunction. Another disadvantage is they need to put in a minus 70. So need to be in a liquid nitrogen bath of 77 Kelvin. So it is also not possible for practical application, because they always need to be dipped in this cold nitrogen atmosphere. And even we use this homojunction laser, they are not capable in operating in CW mode. They can only capable in to work in pulsed mode. So for heterojunction diode laser, the limitation of the homojunction laser has been overcome. So here both light and the current are confined within the narrow zone of the junction layer. So this is the narrow zone of junction, heterojunction. So here in this example, uh, we have used beta gallium aluminum arsenide and indium gallium arsenide. So, and the heterojunction diode laser came into action almost half a decade, more than half a decade later of homojunction diode. So gallium aluminum arsenide has basically a large bandgap, and when there is a large bandgap, this is very natural, the large bandgap means low refractive index. So what happened? Basically, the light cannot escape through the p-sat. From when the light want to go from n-type to p-type, they basically goes through total internal reflection. So the light can only go towards this. And this innovation of heterojunction diode laser got Nobel in 2000 for CW diode laser using heterojunction diodes. So the electrons, and here we understand how the light is confined. Now we need to understand that how the carriers are confined. The gallium aluminum arsenide is a higher bandgap semiconductor, and the electrons that are injected into the junction from the inside, so they lack the energy. So the electrons who goes from this to this, they doesn't have the energy to go up to this. So the electrons will not cross over to this side. So basically, they are trapped here. So this is a single heterojunction laser. Lasers. So for better work, we need to have double junction heterojunction diode. And how we get the double junction heterojunction diode? Basically, P-type gallium aluminum arsenide, and the between there is inter gallium aluminum arsenide, and in between this there is only gallium arsenide. So again the band gap will be like this. And refractive index will be like this. That is refractive index, that is band gap. So the electrons will be confined here and a hole are here. So they can now go here and there. And the refractive index also, the light can only emit from this side only. Light in both sides, they will suffer the total internal reflection. So the both current and light within the lasing volume therefore ensures that the minority of the change carriers recombine here and the emit light. This result is a significant improvement in the performance of the laser by establishing increased electro-optic efficiency and reduced heat dissipation. It is not surprising that room temperature CW operation is readily achievable from a double heterojunction laser. So here can see that homojunction layer has almost more than double the threshold current where it crosses the LED area and goes into the laser action. Now, if this gallium arsenide layer is very small, we'll go to quantum well lasers domain. With the laboratory initial results, we know that of a lower blazing threshold current and high electro-optic efficiency. Electron. Efficiency. Because of the charge carriers and the active layer, the confinement of charge carriers in the active layer between the junction. This enhances the probability of electrons and holes recombining and emitting light that under those total internal reflection within the double ventricle structure and cannot really escape quite naturally. Therefore, the thinner the active layer is, the more likely be the recombination and better the laser performance. Likely it is recombination and better laser performance. And it is possible that with the layered advanced layer deposition technology, we can like fabricate semiconductor layers as thin as tens of nanometer at such a small thickness that is comparable to the probably wavelength of the electron. The quantum size effect sets profoundly impacts the operation of the direct laser. So this is the difference between quantum well-leveled and direct heterojunction. That therefore direct heterojunction, the intrinsic gallium arsenide layer between p-type and n-type gallium aluminum arsenide, it is very large, and this is L1, and the intrinsic gallium arsenide layer which is very thin. So the large and the small is actually not the usual word. The usual word basically is thin and thick. So this is very thin, and this is very thick, and this is almost the equal to the probably wavelength of electrons, and that only it will affect it will act as a quantum wave, and this magenta color is basically the quantum wave portion here. The electrons, like we know that in the band gap, the upper band is the conduction band and lower band is the valence band, and when the quantum wave phenomena kicks in, the upper quantum wave is for electron and the lower quantum wave is for the hole, and the energy levels of the holes in the valence band as well, but only in the direction opposite the direction of conduction band, forming an upside down well. So the direction is upside down, but the here still, when you can see that the first layer here E1C, this is for the electron, this E2C and E3C. E3C is E1C. Here the first layer is E1H and E3H is the highest layer the hole can have. And transition only happen, the combination only happen at the same end. From 3 to 3, from 2 to 2, and from 1. So delta n needs to be 0, and we know in the quantum world how these energy levels have been described. They define n square, pi square, h square, and 2n c square. 2n square. Holes being heavier than the electrons, energy levels are more closely packed in the case of holes. So NH is, so that is why energy level for holes are more packed. The quantized values of electrons can therefore be appropriately tailored to suit the requirement of particular application by adjusting the layer thickness. So for the particular requirement, we will choose. So for transition and we'll change the L accordingly. As for reducing L, the energy levels move away from each other, while the increasing L, the levels approach each other. L, if we increase, then delta E decrease, and when L decrease, delta E increase. Delta E is basically E1, E2 minus E1. So, or E3 minus E2, whatever, the same thing. So when L far exceeds the T-Broglie wavelength of the electron, the levels become so closely packed as to turn an energy band, the signature of the, so this becomes a band. So that is the signature of the double heterojunction band. So this is the working of an quantum well laser. The operation of quantum well laser is like the semiconductor gallium arsenide semiconductor is sandwiched between p-type and n-type gallium aluminum arsenic semiconductors from the active layer and forms the active layer of the quantum well diode. The extreme narrowness of the active layer allows only a low energy level. So only a one energy level is they reside inside both the conduction and valence band quantum wells. When the diode is followed biased, electron and holes injected into the N and P regions of the diode by the battery appear in the energy levels of the respective quantum wells. The electrons and holes can now recombine to produce light with remarkable keys in the ultra-thin active layer. The inherent high electro-optic efficiency of a quantum well laser allows realization of population inversion and internal lasing at a modest value of the bias current. So the quantum well laser has some distinct advantages. The first one is the ease with which the lasing wavelength can be tuned. Like just changing the thickness. The wavelength of the photon emitted from the radiative transition between energy levels E1C and E8C is essentially governed by the energy difference between the two levels. As the energy quantization and thickness of the layers are interconnected, the wavelength of the emitted photon will also depend on the layer thickness. More precisely, the wavelengths decrease with the reduction in the layer thickness and vice versa. And the recombination of electrons and holes are much easier because the volume is much less now. So that is the reason that quantum well lasers can perform at a high electro-optic efficiency even though reduced active volume greatly reverse the mode filling factor. The small active volume, high volume is the maximum optical power that can be extracted. So this is the stacking when the small volume, which is small volume. If we want to have a greater output power, we need stacking of quantum well lasers. Here we can see that 4 quantum well lasers are there, and the stacking has to be parallel. And for the stacking, they are optically coupled, but electronically they are not coupled. Stacking of quantum well laser. They are optically coupled, but electronically non-interacting. The overlapping electron wave function ensures that the energy quantization of individual heterostructures remain unaffected, giving rise to multiple quantum well structures. The strong optical coupling between the individual active layers in conjunction to their integration within a single optical cavity ensures, on the other hand, an output being of good spatial quality. Now we'll go to quantum cascade lasers. So unlike typical semiconductor lasers, wherein light originates from the interband transition involving the recombination of electrons and holes, a quantum cascade laser operates on This is quantum well laser. This is quantum cascade laser. So the recombination between electrons and holes happen in intra-band sublevels. And the spacing between these levels depends on the length. So it is realized by laying a series of quantum wells in this laser, so they are capable of emitting on the need, and they can need an far higher region, and as well as in terahertz region they can emit. And this is the schematic representation of working of quantum cascade laser. Okay. Lasers. So what happened that when we need a more intense light, only one transition is not enough. So for that, we need a cascade of lasers. A single electron upon its injection into the gain region, it goes to a transition and emits a photon. Then that translate into another well and do the same thing. So the same electron is being translated from upper level to lower level multiple of times, and that upper level and lower level difference is same, so they are emitting photon at the same frequency, but only the intensity has been increased in at that time. So these are going, we are doing that to increase the optical power. Now, this is a diagram of edge emitting diode laser. Here, so here what happened that the active length here equals the length of the junction layer, and to clip and end facet with intrinsically high Fresnel reflectivity can perform the role of cavity mirrors. A laser based on such a cavity would thus emit through its ends and is therefore termed as the edge emitting laser. So this is the active region, and there here we put the emit, and basically the length, this length is the active region. So beta aluminum gallium arsenide, and between aluminum gallium arsenide, so there is only gallium arsenide, and that is the active region. To restrict the current flow through the narrow region to increase the density of the charge carriers, the electrical function is taken by laying a strip electrode at all. This is the strip electrode. Here we know that aluminum gallium arsenide has higher band gaps than the gallium arsenide, so light and the carrier confinement will be there, and the divergence to beam of a light is particularly governed by its size and at the source, and the narrower the source, the higher its divergence. So here the active layer is so thin that it will diverge, extremely divergent. But as the active zone is smaller than the vertical direction, then in the horizontal direction, the divergent beam is essentially elliptical in shape. So to overcome that, we go to surface emitting diode. So here you can see the mirrors are here and here. That reflected rear mirror and front mirror. There the mirrors were on that side, here and there. So that is longitudinal configuration. Longitudinal configuration, and this is transverse configuration, and here we like solve the problem of a age emitting diode and the spatial quality has been improved here. Spatial quality of the beam has been improved. And this is actually called VPCSEL, vertical cavity surface emitting laser. Now, if we want kilowatt, the type of power from the semiconductor diode laser, we need to use laser diode arrays. For kilowatt level of energy. That can be done as a stack side by side as well as atop each other. Stack diode laser side by side. As well as atop each other. Now we'll go through some questions. Question number 1. Holes in valence band give rise to flow of current K with increase in temperature, the in presence of external electric field, C. In the absence of external electric field, D is wide open. So the hole is the absence of an electron in the valence band. In a semiconductor, the semiconductor electrons in the neighboring covalent bonds can jump into the vacant place. When this process repeats, the wheels appears to move in the opposite direction. But for there to be net current, the motion must become directional. This happens when an external electric field is applied. Without an electric field, we will still have random thermal motion. Without electric field, we will have random thermal motion. So, no drift current. But when an electric field is applied, we will get the electrons shift opposite to the field poles actively drift along the field and the current is produced. So, answer is in the presence of external field. Question number 2. Doping of trivalent impurity into silicon will give rise to an extrinsic semiconductor with predominant charge carriers as holes, electrons, C, holes and electrons, D, ions. So a trivalent impurity like it means 3, which is here. Aluminum is a trivalent impurity, as well as this gallium. So basically, that will rise to an charge carrier, negative charge carrier will be in that case this holes. 3 electrons, that is aluminum, gallium, and so on. Question number D. A depletion layer that is formed at the junction of P and N semiconductor A has both electrons and holes as charge carrier. B has electron as charge carrier. C has no charge carrier. D has both as charge carrier. As a joint, electron diffuse from N side to P side and holes diffuse from P side to inside. So electron goes from this and hole goes from there and they recombined, and in the depletion region here we will get fixed positive sign and positive carrier and fixed negative etc. and on the P side. So there is no, we have fixed carriers. So the correct answer is has no charge carriers. Question number 4 is width of the depletion region of PN junction increases with increased doping concentration. Increases with reduced doping concentration is independent of doping concentration. D, none of the above. So the depletion width depends on how much charge is needed to establish the junction field. If doping concentration is high, many charges are available in a small distance, so depletion region can be narrow. If the doping concentration is low, fewer charges are available per unit volume, so the depletion region must be spread over a large distance. So that is why the answer is increases with reduced doping concentration. Question 5. Junction, diode laser, threshold, is confined in the junction. Charge carriers are confined at the junction. C. Both light and charge carriers are not confined at the junction. B. Both light and charge carriers are confined at the junction. So basically, we know that in junction diode laser, nothing is confined in the junction, and that is why we needed the heterojunction diode laser, so that we can confine the light and also the carrier and reduce the optical loss. For a PN junction to be able to emit light, it has to be forward biased. B has to be reversed biased. C need not be biased. D none of the above. So we know the PN junction to be able to be like we need to be it in the forward bias. So basically, for the light emission, electrons and heavy must to be injected toward the junction, and they needs to be recombined efficiently, and that happen only the forward bias is happened. Question number 7. for a PN junction to act as an LED. The semiconductor has to be of direct bandgap type, B of indirect bandgap type, C overlapping condition, overlapping conduction, imbalance, Randolph, D none of the above. In a direct binder semiconductor, the conduction band has minimum and valence band has maximum of at the same crystal momentum, and we need that. Otherwise, and in the direct bandgap type, momentum conserved. So all the excess energy to conserve the energy will emit as a light. For indirect bandgap, that is not going to happen. The thermal emission is going to happen here. So we need direct bandgap type. Question number 8. In a direct bandgap semiconductor, during recombination, only energy is conserved. Only momentum is conserved. Both energy and momentum is conserved. The energy and momentum are not conserved. We know that for direct bandgap, both energy and momentum conserved, and that's why we get the light. So that is for today, and there is an extra class, and I'll recap all the main concept of this course there. So that's for today. Thank you.